Welcome back to Introduction to Organic Chemistry 2330. We're going to go ahead and continue on with our week 7. The only thing we have to do this week is, of course, get our, homework done for Chapter 8 on Friday. Chapter 10 homework is due next Friday. And then the Chapter 9 homework, because 9 is about benzene rings, and we have a whole bunch of new stuff there, won't be due until the following week, which is kind of before our next exam. Okay, so we should be all the way through chapters 8, 9, 10, and 11 before our next exam, which is on October 28th, Wednesday. Okay, so due this week includes the homework on Friday, and then go ahead and start reading Chapter 9 for Monday. Chapter 9 is kind of complicated. We have to worry about aromaticity, the rules of aromaticity, and how to name things. It's a little different than what we've been doing up to now, which is why I kind of wanted to get the alcohols and thiols and amines all done at the same time, because they all have interesting connections as far as their atom to hydrogen bonding goes. And that's the very interesting thing there. So any questions about that or the administration or chapter 8 before we begin? Okay, while you're typing those questions in or trying to, I will go ahead and share my screen for our chapter 10.
I have a question for chapter 10 really quick.
Okay. Please go ahead. I heard you ask the question. Did everybody else hear the question? I did not hear a question. Getting a little bloop, bloop, bloop. So, yeah, I'm not, are these the goals or the notes, video notes? Okay, I will be presenting from the full slides on this. There are the goal slides on Top Hat as well. So this is going to be the full lecture, but then the other ones are going to be on the other part.
Like the last chapter was more of like the chapter overview rather than.
Correct. That is going to be that way for the next 2 chapters. Because there's so much, I want to actually do the full lectures for these and see, you know, how the homework grades and the other grades go after that. Okay. All right. So these are the full slides that can be found on Canvas. The goal slides are the ones found on Top Hat. So they're slightly differently. These are like the full video slides you see on the Introduction to Organic Chemistry Brown and Poon channel on Top Hat. So I'm not sorry, on YouTube. So that's what I'll be going over today. Okay, so last time we talked about alcohols and thiols, and the key there was that we had some atom other than carbon bonded to a hydrogen, and those bonds are more polar than the carbon-hydrogen bonds, at least in the case of the oxygen, and about the same polarity as with the sulfur and hydrogen bond. Here we're going to talk about amines. Amines are close to carbon, and so if we're looking at the periodic table, we have a fluorine, which is the fluorine hydrogen bond is more polar than the oxygen hydrogen bond, which is more polar than the nitrogen hydrogen bond, which is more polar than the carbon hydrogen bond. So just moving along that row, we'll see that the difference in electronegativity changes, and that changes their properties, meaning that oxygen hydrogen bonds stronger than amines do because the polarity is not the same. Okay, so let's get into what we mean by amines. Amines are an entire class of chemicals where we have nitrogen in the system. And so Technically, the simplest version of this is not an organic molecule. The simplest version of this has no carbon in it, and it's called ammonia, okay? So in this case here, this is where all of our amine compounds can be made from ammonia by reacting it with other carbon compounds. Now, unlike alcohols, where we classify the alcohol as primary, secondary, and tertiary based on the number of carbons attached to the carbon the alcohol is attached to, we're actually going to do it backwards. In this case, we're looking at the number of carbons actually attached to nitrogen. Okay, so that means that if we had a primary amine, that means we only have one carbon attached to that nitrogen, and that means we have two hydrogens. Okay, and if we have a secondary, that means we have two carbons attached, and now we only have one hydrogen. And when we have tertiaries right here, that means we have three carbons attached. Okay, so in all of these, we still have our lone pair, and our lone pair we got to play with here because that is our place where we have our base come from. So it's a Lewis base because it has that lone pair, and it acts as a base most of the time. And we'll see that we can change that base strength by other properties of the compound. Okay, so because they're classified as primary, secondary, or tertiary, and think about that as, just how many carbons are attached to that nitrogen. Okay, it's the only one in the system that does that. Carbons and alcohols are known the other way. Okay, so up to now, we've only talked about aliphatic systems, which are things with only carbon and hydrogen, and things with only alkyl groups. However, we also have what we call aromatic amines, and aromatic amines are those which have a nitrogen bonded to one or more benzene rings. Now we're going to look at benzene and all the different derivatives of benzene next week. But what I want to draw your attention to is this ring of 6 carbons with these alternating single and double bonds. This is benzene. And this is what makes the difference between just an aliphatic group, like this methyl group here, and the aromatic group, which is the phenyl ring. Anything with a benzene on it is considered aromatic, okay? So, but then we also have a third class of materials. That third class of materials is what we call heterocyclic amines, which means we have a nitrogen in a ring with some carbons in it. So if we were to classify these 3 compounds right here as aliphatic or aromatic or both, we would have to look at what's directly attached to the nitrogen. In this case here, we have a benzene attached to the nitrogen, which makes this an aromatic amine. Okay, so things that have benzene on them have really interesting smells, and so they're called aromatic. Okay, in this case here, we have a benzene directly attached, but we also have an aliphatic directly attached, and therefore this is an aromatic amine because it has the aromatic ring on it. Okay. However, if we put a little spacer in here, this CH2 in here, and we only have these other aliphatic, this is now turned into an aliphatic amine. There is no benzene directly bonded to the nitrogen, and therefore it is an aliphatic amine. Okay. Now, one of the reasons we're drawing the distinction between aliphatic, aromatic, and heterocyclic amines is that it changes their basicity, changes their ability to act as a base, and so we need to make sure we can classify them as such. Okay, so now we have those 3 different classes of amines. Let's look into the last set here, which is the heterocyclic amine. So the idea is the heteroatom is something different than carbon. So that's what hetero means. Cyclic means it's in a ring. And so we basically have replaced one carbon in that ring with nitrogen, and therefore we have a heterocyclic amine. Now they come in 2 different ways. One way is that you can have this aliphatic, meaning there's no aromaticity, and we'll learn about aromaticity in the next chapter. And then we have one that are aromatic. And so the ones that actually have rings, and we have a total of 6 electrons in these rings, giving us our aromaticity. Okay. So we now have really 4 different classifications. We have aliphatic amines, aromatic amines, heterocyclic aliphatic amines, and heterocyclic aromatic amines. Okay. And again, the different classes have different basicities, which is what we'll get into in just a little bit. Okay, so let's go ahead and look at a few examples and then classify these as primary, secondary, tertiary, or aromatic heterocyclic or aliphatic heterocyclic, okay? So if we look at this first one here, we only have one nitrogen in here, so we have this nitrogen here, and it's bonded to sp2 hybridized carbon, sp3 hybridized carbon, which makes it aliphatic, sp3 hybridized carbon, which makes it aliphatic, but it's still in a ring. So this makes it in an aliphatic heterocycle, cyclic amine. Okay, so it's in a ring, it has no aromaticity, and it is an amine. So it's an aliphatic heterocyclic amine. All right, let's go to the next one over here, nicotine, which is found in all of those cigarettes and vape products here. We actually have two different nitrogens here, so we have to classify them differently. If we look at this one right here, this is a nitrogen in a ring, but it's an aromatic ring. So this is our aromatic heterocyclic amine. And this right here, this 5-membered ring here, has no aromatic, has none of these double bonds associated with it. So therefore is an aliphatic heterocyclic amine. Okay. And then if we look at this last compound here, and we look at this and you go, well, okay, there's only one nitrogen on the whole thing. It's right here. And it's got 3 different aliphatic groups attached to it. So this is an aliphatic heterocyclic, because it's part of these, both of these 2 rings, amine. So that we have a way to classify our aromatic and aliphatic amines and identify them based on whether or not we have these alternating single and double bonds in our, if our nitrogen is in a ring with alternating single and double bonds, chances are it is an aromatic aliphatic amine. Okay, so we have aliphatic amines, which only have sp3 hybridized carbons. We have aromatic amines, which are those that have a benzene ring attached directly to the nitrogen. And then the last class is the heterocyclic amines. And we have 2 types of those. One is they do have alternating single and double bonds and the nitrogen in the ring. So we call these aromatic heterocyclic amines. And if they don't have that alternating structure like the other 2 here, we call those aliphatic heterocyclic amines. Okay, does that answer your question? Okay. All right. So that being said, how do we name these? Well, the aliphatic amines are actually named fairly simply. If it's the highest order group, and really it's even below alcohol. So this is like, if there's anything else on there besides that amine, it's going to be named for the other compound. So, but if you only have an amine on your system, what you do is you drop the E at the end of the word and you add amine. So in the case of this right here, we have 4 carbons, which would be butane. Drop the E and add the word amine. Okay, so so when we look at that again, so let's name this one right here. We have the longest aliphatic chain right here is these 2 carbons. And the phenyl ring right here is a substituent, unless it's named for that compound. And we'll show you one of those in a minute. And so we have ethane amine. Ethamine is there. And then we have a phenyl group in that 1 position. Okay. And the amine is on this position, suggesting that this is our number 1 carbon and this is our number 2 carbon, because the compound is named for the amine and we want it on the lowest carbon possible. So here it can't be on the 1, so it has to be on the 2. Here we assume it to be on the 1. Okay. Now, just like in the case of alcohols, more than 1 alcohol in a ring, we use the exact same thing of di, tri, or tetra. And just like in the alcohols, we put the E back on and then just add di, tri, or tetra. In this case here, we have a 6-membered chain right here with an amine on the 1 carbon and an amine on the 6 carbon. So it's the 1,6-hexane diamine. Okay. So that's how we name aliphatic amines by the IUPAC method. And then there's also a way to name it where we have the IUPAC method for the material called aniline. So in this case here, we have our simplest aromatic amine, which is a benzene ring attached to a nitrogen, and we call that compound aniline. Okay, it has a special name. That nitrogen changes the name of the compound, and that's how it's named. Now, once we add groups to that, we actually have to identify where those groups are. So this is our 1 position, 2, 3, and 4. So we have 4 nitro aniline. And if we have a methyl group on there, we do it the same way. We number it around, 3 methyl aniline. And if we have any other group there, we just show the position as 1, 2, and 3, 3 methoxy aniline. So this is a special name for our aromatic amine, and that retains its common name in the IUPAC system. So you'll name it for the aniline if you see that functionality. All right. So because the amine is one of the lowest functionality groups, it's typically used as a substituent. So in the case of this simple one right here, we have 1, 2 carbons, so that's ethyl right here. Alcohol is higher priority than the amine, so we call it for the ethanol. So it's ethanol right here. And then our amine is our substituent. And since we're naming it for the alcohol, we number it 1, 2. We have 2 amino ethanol. Now, in the case of an aromatic system, carboxylic acids, of course, are one of the highest priority groups. So we name it for the carboxylic acid, and we attach the amine as a substituent in its correct location. We'll learn more about numbering around these benzene rings in the next chapter. Okay, so if we wanted to name them not by the IUPAC name, but the common name, what we do is we name or list all the different groups attached to it and call them the alkyl groups. So they would be like a substituent on a main chain where we add the YL at the end of it. So for example, if we had just a methyl group on this nitrogen here, we call it methylamine. If we had just an ethyl group, we'd call it ethylamine. And if we just have one group, we can just say whatever it is and add the word amine at the end. Okay. Now, if you have 2 things and they're the same, you can use di with whatever that pendant group is and then amine at the end. So in this case, we have 2 of these cyclopentyl groups. So we have dicyclopentyl amine. And if you have 3 of the same groups, you just have to do tri and whatever the alkyl group was. Now, if they're different, you have to name them separately and in alphabetical order. So if you had ethyl methyl butyl, you would name it butyl ethyl methylamine. So, okay. Now, because that nitrogen has that lone pair, and because nitrogen can act as a Lewis base, it can actually bond a 4th time and get a positive charge, okay? So whenever we bond that nitrogen a 4th time and we get a positive charge, we call them amine salts, and they're typically called ammonium salts, okay? So in the case of the aliphatic systems, we're calling this ammonium salt. So here we have 4 methyl groups on there, so tetramethyl. Ammonium, because our nitrogen has 4 things bonded to it and a positive charge. And then whatever the counterbalancing ion here, in this case it's chloride. Now if we look over here, we have slightly different, we have an unsymmetrical one. We have this group right here, which is called the benzyl group. But then we have the 3 methyl groups here. So it's benzyl trimethyl. And again, our ammonium for the nitrogen with 4 bonds and a positive charge. And then our counterbalancing ion here as the hydroxide. So when we had the pyridine or the aromatic amine, like this right here, it still has a lone pair, but it already has 3 bonds to carbon. So that by just bonding something else to it out here, turns it into a different material. It still uses those electrons to make that new bond, and it still has a positive charge. But in this case, we name what the alkyl group is. In this case, it's the hexadecyl, which makes it 16 carbons, hexa 6, decyl 10. And then the salt becomes part of the heterocycle here, which is called pyridine, so it's pyridinium. And then we have our counterbalancing ion here. So that's how we name salts of nitrogen. Now notice all of these, the nitrogen has a positive charge and there's always a counterbalancing ion. Excuse me. All right, so there's not that many rules when naming the amines. Most of the time they'll probably be named by their simple aliphatic names like triethylamine or methylamine. Mold must be high. Excuse me, sorry. Okay, so I was talking about how the amines have a polar bond between the nitrogen and the hydrogen. And that means if there's a hydrogen on the amine, it will hydrogen bond. So it can hydrogen bond. However, because the polarity between the nitrogen and the hydrogen is weaker than that of the oxygen and hydrogen, there's less of a difference. It actually makes it hydrogen bond a little bit less. And if it's hydrogen bonding less, that means it changes the properties less. Okay, again, this is only the primary and secondary amines. If you get to a tertiary amine, there's no hydrogen bond. Okay. So let's look at that effect just from the bond strength. So we have something that's pretty close to the same molecular weight, and they are pretty close to the same structure there. They have a methyl group, and then they have that. And so the molecular weights are almost identical, only one off here. However, because the OH has a stronger hydrogen bonding capability, it actually boils 71 degrees higher than that of just the methylamine. Okay. In fact, the sulfur compound, which has an even less polar bond, actually boils much, much lower at like -37. So that shows you the difference between sulfur and hydrogen, which barely hydrogen bonds, the amine hydrogen, which does a moderate hydrogen bond, and the OH, which does the strongest hydrogen bond, just like we find in carboxylic acids, but we'll talk about that in a later chapter. Okay, that being said, those amines, especially the primary, secondary, and tertiary amines, all have a lone pair. And because of that lone pair, they act as Lewis bases, okay? Now, what that means is we can actually have the amines dissolve in water. And when they do, they will act as a base and deprotonate water and give us our salt, which is our ammonium salt right here, because now it's positively charged with a new bond to hydrogen here and a counterbalancing ion here. Okay. So how do we know how far is this equilibrium going to lie? Okay. So we have to look at our equilibrium constant. And so we have our conjugate acid right here. This is our conjugate acid and our conjugate base, and this is our base and our acid right here. So by comparing the concentrations of each of these, we can get that equilibrium constant. Okay. But that doesn't really tell us, empirically how far or we would want to go back and forth. So we actually start to look at how basic the material is, basically how strong it is. And the way we can derive that is that the pKa scale that we're very familiar with right here, turns out pKa plus pKb equals 14. So even if you don't have a pKb scale, you can calculate out what the pKa of that particular compound is. Okay, so in this case here, if we took this right here and we had our conjugate acid in the presence of water, and we made our base and our conjugate acid here. Notice water is not on the bottom here. When you have something dissolved in water, you typically remove it from the equilibrium constant. Anyway, when we do this and we take our log of it, we find out that the pKa of this compound right here is 10.64. Okay, so the pKa of that protonated amine is 10.64. So water is about 15 and carboxylic acids are about 5. So it's somewhere in between those two. Okay. So if that pKa is that number, approximately 11, that means its pKb is going to be 3.36 because they are additive. Okay, so that's how you can relate the pKa to the pKb. And when you look at tables of amines, when they talk about basicity, they're almost always listed in pKb. Okay, but knowing this relationship here, you can always translate it back into our pKa scale and let it compare with other things. Okay, so why would we need to do that? Well, what if we wanted to see which direction the equilibrium lies? Okay, so in that case here, we're used to using the pKa values and looking for it to go from the strongest acids to the weakest acids. And we know that the equilibrium always lies toward the weaker system. Okay, so we have to figure that out using comparing just the pKa's. Okay, so we don't know the pKb of this, but we do know the pKa of this conjugate acid. All right. So that means we can take whatever the acid is on this side of the equation, in this case it's acetic acid, and whatever the acid is on this side of the equation, in this case it's the ammonium salt, and therefore we can see that the pKa of acetic acid is lower than the pKa of the ammonium salt. So that means it's the stronger acid. Now, equilibrium always lies to the weaker acid, which means the equilibrium of this reaction lies in that direction. Okay. So that way we only have to really pay attention to our pKa scale and be able to still get a prediction about which direction things are going to lie. Okay. So that being said, I want to show a compare and contrast of the different types of amines within their own group. And don't worry, I'll blow this table up here. And so what I want you to see is that the aliphatic amines are always stronger than their aromatic amines, and they're typically stronger than their heterocyclic amines, their heterocyclic aromatic amines as well. Okay, so let me pull up this table real quick. And to give us a starting point right here, let's look at ammonia. Again, it's not an organic molecule because there's no carbon in it, but it has a pKb of 4.7, which makes its equivalent pKa, its ability to, have an acid come off there as 9.26. Okay, so that's just kind of our starting point. Okay, so just like on the pKa scale, the lower the number, the stronger the base on the pKb scale. So the lower the number, the stronger the base. So if we look at the primary amines here, they're actually lower than ammonia by itself. Okay, which means the primary amines are actually more basic than ammonia. And this has to do with the idea that it can have some electron density from that carbon, helping it have a higher electron density on there, and therefore it is more basic. Okay. Now, if we move to our secondary amines, it really doesn't change that much. It goes down a little. It becomes more basic because we have a little more donation going on there, and we have still at basic system. And if we go and add a third one here, it stays in the same range. So all the aliphatic amines are more basic than ammonia. In fact, all aliphatic amines are the most basic of the amine set. Okay, so if we go and look at the aromatic rings, we actually see some interesting shifts around. First of all, just adding the benzene ring there decreases the basicity. The number went up. So it's less acidic, less basic, more acidic as the conjugate acid. This has to do with the idea that you can delocalize this electron pair in the ring here and pull some electron density out so it becomes less basic. Now that same concept means that if you have something that's a donating group, it's going to make it a slightly more basic. But if it's electron withdrawing groups, it's actually going to become less basic. So by taking away more and more of these electrons from that nitrogen makes them less basic. Okay. And so the last two I have here are what we call heterocyclic aromatic amines. So they have the, there's a lone pair right, ooh. There's a lone pair right here on this nitrogen here. And what we see is the aromatic amines are slightly more basic, slightly stronger basic than the aromatic amine itself, like aniline, but it's not as basic as the aliphatic system. So it's somewhere right in between. So if we wanted to rack and stack on this and a general trend, aliphatic amines are the strongest bases, weakest conjugate acids. The heterocyclic aromatic amines are the next strongest. And the last ones, the weakest bases, are the aromatic amines. Okay, let's see. What am I on time? All right. So let's figure out why. Okay. So aromatic amines are considerably weaker bases than aliphatic. And we know that because when we actually do this equilibrium and we measure this right here, and we measure the pKa of these conjugate acids here, we get the idea that we can get our this pKb is lower than this pKb. So this is the stronger acid. And I'm sorry, this is the weaker acid, stronger base. And we see that the aniline system here is analogous. And so this is the stronger base and this is the weaker base. But why? Okay, the reason that the aromatic amines are weaker bases than the aliphatic is because we can take those electrons off of that nitrogen and add a resonance structure to the benzene ring. So there's less time for those electrons to act as a base. And there are a significant number of resonance structures that if we pull these electrons down right here, we end up with a positive charge, at least part of the time, on that nitrogen. Okay? Because there's part of the time that that nitrogen is positive, it is less basic. It has less time for these electrons to reach out and grab at acids. Okay. Now, if we look at an analogous one, which is aliphatic right here, there's nowhere for these electrons to go. There's no double bond for them to share with. There's no way to delocalize them. And because there's no way to delocalize them, that means these electrons stay here the whole time. And because they're there the whole time, they act as a stronger base. Okay. So now I said on that table before that the electron withdrawing group can decrease the basicity again. So this is more of an inductive effect as well as a resonance effect that we saw in the other. Just having the aromatic ring gives you resonance structures, gives you resonance structures that allows there to be a positive charge on that nitrogen. Well, when you have an electron withdrawing group here, you actually also have an electron inductive effect, pulling some more electron density away from this lone pair here. The less time there's a full lone pair there, the less basic the amine becomes. Okay. So let's take what we just learned about aromatics and aliphatics and apply that to just looking at what we think is the more basic one of the set here. So in the case of A right here, okay, is, well, let's call this number 1 here. Is A or B the stronger base? Go ahead and put it in the chat. Okay. So one looks kind of like maybe an aromatic amine, and one looks kind of like an aliphatic cyclic amine. So yeah, lots of B's there. You are correct, because the aromatic amines all are less basic than our aliphatic amines, even in that ring structure. So because this is an aliphatic, even though it's a ring, it is going to be the stronger base. Okay. All right, now I'm gonna trick you here. On part 2, which is the stronger base? Is it C or D? Got to think about, okay, is it aromatic, or is it aliphatic, or is it heterocyclic? Come on, get some more answers here. C maybe? All right, come on, more. Lone pair, okay. That lone pair can be delocalized through the ring here. This lone pair, ooh, can't. So this having no double bond that these electrons can share with right here makes those electrons stay there more often, meaning D is, number 1, it's aliphatic, because that CH2 is aliphatic, and therefore this is our aliphatic amine, and this is our aromatic amine, making this our stronger base. Okay, so don't let the ring fool you. You have to look at exactly where it's attached. This is attached to an aliphatic group. That makes it a more basic amine. Okay, great. At least some of you are awake. That's great. All right, so if delocalization can hurt our basicity, can we also use it to help our basicity? And the answer is yes. In the case of guanidine, this is a naturally occurring product. It's used in a lot of biological systems here. We actually have 2 amines plus an imine, which is this carbon double bonded to a nitrogen. Okay. And it can react with water to protonate to give it a positively charged salt. Okay. And the pKa of this is 0.4. Okay. So that's the strongest, most basic thing we've seen so far. Okay. Ammonia was like 4, and the aliphatic amines were in the 3 range. This is almost 0. Okay. So this is the strongest base we've seen so far. But why? We have the ability to share the charge around multiple nitrogens. So because we can share that, because we can resonance delocalize that positive charge over 3 nitrogens, that makes it more susceptible, more likely to act as a base. And anytime you're more likely to, anytime you can share electrons, it makes it easier. This is exactly the same as why carboxylic acids are so much more acidic, because they can delocalize that negative charge over 2 oxygens in that carboxylic acid. In this case, because we can share that charge over 3 nitrogens, it becomes more basic. So delocalization helps you in the case of if you can spread the charge out over those atoms. Now notice we're spreading out our lone pair here. Our lone pairs are spreading out here. In the case of that in the case of the aromatic amines, we're actually not spreading that lone pair. That lone pair is coming into the ring and leaving a positive charge on that nitrogen. Okay, so that's different. We're doing a different type of delocalization, which is why the guanidine is the most strongest base that we have in our system. Okay, so we don't have that many reactions we can do with amines. Okay, one of the things we talked about in our substitution reaction was we can use it as a nucleophile. Okay, so that's one thing we can do. But the other thing we do with these amines is we can make them water soluble by reacting them with strong acids. Okay, so this is norepinephrine right here. This is a commonly used pharmaceutical. It does not dissolve in water. It dissolves in water very poorly. So if you were trying to take this as a pharmaceutical to get it to absorb into your mouth and or a body into the blood, it really is poorly soluble as it's made with its just free nitrogen. However, if you take it and add a little bit of HCl to it, it becomes the ammonium salt right here. And most ammonium salts are very water soluble. Now, that's why if you look at this, if you looked at a bottle of your medication here and it says neonephrine hydrochloride, they're doing that to make it soluble. And you'll see this in a lot of different things. I have a nasal spray that's the hydrochloride. I have another thing that's the sulfate. These are all different things that are made water soluble, absorbable through our membranes because they're made with the water soluble salt. Okay, the more classical example is cocaine. Cocaine as a powder is the hydrogen sulfate salt, so it's sulfuric acid salt of that. But if you take away the sulfuric acid part and make it into its free amine, that free amine is actually known as crack. So, and it's easily sublimable. So one is water soluble, one is water insoluble, and they're both the same basic drug. So, but don't do that. Anyway, so again, it's kind of hard to make primary amines for a couple of reasons, but one of the easiest way to make a primary amine from an aromatic amine is to actually take a nitro group and to reduce it down. So we'll find out in the next chapter that we can add nitro groups to carboxylic to these benzene rings. And one of the things we can do is we can actually take that nitro group and turn it down to an amine. This is probably the best way to get a primary amine on an aromatic ring. Okay. So I said it's kind of hard to do primary rings. It's like, well, what if we wanted to do just nucleophilic attachment? We saw that amines act as nucleophiles and that we can go ahead and use it to attack things and displace it and form a new carbon bond. So if we did that, let's say the first step of that reaction would be our lone pair is acting as our nucleophile to reach out and grab at this carbon right here to create a new sigma bond. So once it did that, it would form this intermediate here. And then of course, the next thing we would do is we have that, step one is one of those things we can do, which is reactant electrophile with nucleophile. The next thing we'll do is we'll take away that proton to turn it back into a neutral amine. Now, when we do that, this is still a nucleophile, okay? It still has that lone pair. It can still go and attack another one again. So even if you only wanted one on there, I think that you would end up getting another one on there and another one on there until you completely consume whatever your electrophile was. Okay, so because each time you react it and each time you lose that proton, it becomes a nucleophile, it becomes very difficult. You can start with a ammonia and get a primary, a secondary, and a tertiary, and a salt, all from the same reaction mixture. So that makes it very difficult to stop with just a primary aliphatic amine. Okay. So that is the end of amines. Any questions on that? So we're a little early, but the amine chapter is quite short. And so the big things are, classifications and basicity. And so if you go to the goals for our things, we're going to look at nomenclature and properties, which includes that hydrogen bonding aspect. We're going to look at the basicity and the basicity scale. And there's not much on the reaction side. So there are very few reactions to play with. Okay. And that is all I have for today. So go ahead and ask questions. I guess you should ask it in the chat room because my internet connection is a little unstable. Okay. Now, don't go forgetting everything over the weekend. Go ahead and read chapter 9, benzene and its derivatives. Okay. If you have to run off to some other class or do some homework, go ahead. If you want to stay behind and ask some questions, we'll see if maybe the fewer number of people connected will allow me to answer questions. Thank you. Homework 1429 and the homework 1523. All right, let's go to, let's see if that would be this class. All right, I'm pulling up those two homework questions. The first one we got was the 1523. Yeah, my connection's a little slow, even my thing's steeping here. Okay. All right, we got 1523 and 1429. So 1429. Okay, that's the first one I came to, so I'll answer that one first. What is the major product of the reaction given? Oh, interesting. So in that one, let's see, we had a special reagent we used because when we had an alcohol, if we had a tertiary alcohol, all we had to do was add a little bit of HCl to it, and we can make that tertiary alkyl halide. But because it could form the carbocation. In this case here, we cannot form a carbocation, so we have to use a special reagent to replace that OH with the chloride. So in the case of this, we have that SOCl2, and pyridine is just the catalyst. And so the SOCl2 will take away the OH and add a chlorine to that bond. So that should give you an idea of what the product is there. Okay, does that answer your question?
I don't.
All right, you're gonna have to type it into the chat. Sorry, it's still, it's going on. Whoa, whoa, whoa.
If you can hear me, but yes.
Okay, yeah, I heard you that time. Great. All right, so let me go ahead and go up to 1523. 1523, ooh. Select the reagents that would promote the following transformation most efficiently. Okay, so let's see. So we want to form an ether. We only saw one way to form ethers, right? So we had the alcohol act as a nucleophile and displace an alkyl halide to create that new. So we need to create an alcohol first. And then, ooh, notice that one side of it has 2 carbons on it and the other side of it has 3 carbons on it. Okay. Oh, is he not here? Did Joel head out? Yeah, okay, he'll email me later. But anyway, this is an interesting one because what that says is that you had to knock off this chloride to create a salt first. then you have to react it with something else. So it looks like you probably, you can't do it with that. It's probably A, because you don't need to, we haven't even made Grignards yet. We haven't made peroxides yet. We haven't done the borane yet. So that's an interesting question, because it's got to be A, because those are the only reagents we had to work with. So, okay. So thank you very much. If you want to hang behind for a question, go ahead and type it in the chat. Other than that, let's go ahead and close it out and upload this video if you couldn't hear me very well. All right. Thank you. Bye. Oh, you have a question about lab? Okay. I think I emailed about that.
So
I'm sorry.
can you hear me?
I heard that part.